name is Donna Grari, and I'm here today to talk to you about mixing crowd and algorithm efforts to segment objects in biomedical images. So the motivation for this work is that many researchers are trying to get a better understanding of what's going on inside of organisms. For example, some researchers are trying to quantify the effects of cancer drugs to help save more lives. Other researchers are trying to understand the basic principles of how embryos grow into organisms. And additionally, other researchers are trying to engineer the environment to control how genes express themselves, for example, to improve the health of people. So there's a whole foundation of research which is premised on the things we can see, we can understand. So we can, as humans with our eyes, see the organism, but with certain devices we can look deeper and deeper within the body at smaller and smaller objects, moving from the organ systems to organs, to tissues, and finally the individual cells that make up all these different layers. And the first problem underlying these research projects is how to find the objects. And in particular, I show here for the three projects I spoke of, the attempt to find the boundaries of the cells that are making up the larger structures. So given that that's the key for a starting point for these projects, we face a challenge as a community, which is how do we choose a method? And in particular, we understand that experts are very expensive, so there's been a whole lot of effort to try to find different algorithms to automatically pull out the the boundaries of objects. So I show here examples of two popular tools. One is Fiji, and you can see a whole list of different options. Another one is called CreaSeg, and this includes 6 different options with many different parameters to tune. So for people who are non-algorithm specialists, they face the challenge of which algorithm, if any of these, will work to pull out the boundaries of the objects in their images. And the second challenge is, given this new emergence of crowdsourcing as an option to demarcate objects and images, how best to employ crowd efforts. So we know we have experts, which are the gold standard. We know we have algorithms, which are plentiful, which often serve as the bronze standard. And in between these two extremes are the crowds, which are typically untrained. In prior literature, it suggested that they do better than algorithms, but less good than the gold standard of experts. And in this work, I'm going to explore how best to employ crowd efforts with a focus on crowds from the Amazon Mechanical Turk platform. So, given these motivating questions, the key contributions and findings from the work I'll present today is a new segmentation framework that links algorithms and crowdsourcing efforts. We'll also show by the end how to improve the segmentation results over relying on the best of 11 standalone algorithms. And lastly, how to produce expert quality segmentations with algorithms and crowds. So diving in. In this work, we propose a framework we call SAVE, and I'll also describe some of the implementations. So just as a backdrop, today's standard approach is that given an image, we take one annotation collection approach, whether it's an algorithm or a single crowd worker, ask either the algorithm or the crowd worker to demarcate the object, and output, we get a binary image showing the object of interest. So instead, what we propose here is, given a raw image, we attempt to collect multiple annotations, S we put here, and that can either come from S different algorithms or S crowd workers. Then a next module tries to vote on which to use. So computers can be used to do the voting, or again, crowds can be used to do the voting. Finally, an evaluation step is done, and output is a single segmentation result. So to make this more concrete, we actually explored different implementations of our SAVE framework. So in order to build the system, we looked at 11 different algorithm options, which span the older thresholding-based methods up to the newer level set-based deformable model methods, and those were all candidates within our SAVE system. We also permitted the use of crowds using LabelMe. So LabelMe has been around for almost a decade now, and it's been a very popular thrust within the computer vision community for how to pull out boundaries of objects. And what you can see here is an example of someone clicking around the boundary of a cell. So this is the tool that we use to enable crowd workers to demarcate objects. The next step is to collect votes. So our implementation for the algorithms was to have majority voting from the individual, from each of the resulting annotations. So here, I show examples of multiple annotations, and so every single pixel will vote what should be the output result in the resulting segmentation. So we show here there's 2 votes that the cell should be white or background, 1 black or foreground. The resulting cell is background due to majority vote in this example. So that's the computer voting method we use. And finally, we designed our own voting method for crowdsourcing. The key, we show here an example of choosing between 5 different options. We overlay the segmentations using a green overlay mask on the original image. The person votes by selecting one of the radio buttons to the left of the image, and then can submit the result. So that was our crowdsourcing implementation. So that sets up our SAVE framework and our 4 implementations and our multiple possible implementations. So now let's talk about how it works in practice. So to explore the benefit of our system, we evaluated our system as follows. First, we chose a data set that is that's pretty diverse in terms of the shapes of objects. So we have from very round to lots of protrusions, very different intensities, so from strong white foreground against a background to mixed gray values. Background clutter can be observed in these images, and there's also boundaries of objects that are hard to detect. So these are some of the challenges in the data set we chose for our experiments. And for our evaluation methodology, we followed the standard protocol of given an image, run an algorithm, you get an algorithm result, compare that algorithm result against a ground truth, choose an evaluation metric to say how similar is that algorithm result to the ground truth, and you get a score. So for evaluation, we chose as our ground truth what was provided in this data set we use, which is to take multiple annotations from different experts and fuse them into one ground truth that reflects the majority opinion. And in terms of our evaluation metric, we use the standard intersection over union measure. So as an example, I show here the ground truth, possibly an annotation by some expert, and the intersection over union metric will look at how many pixels are in common, which is reflected by the dark green, over how many pixels are in total across the 2 segmentations. And in this example, the result is 70% IOU measure. Okay, so now we have our data set, we have our evaluation framework. We first want to explore how are today's traditional approaches working. So we're going to explore 3 baselines. The first baseline is the target performance, and in particular, how do experts do? So we first evaluate annotations where we collect annotations from 3 different experts for 305 images in our benchmark. And what we find here is that the median score is nearly 90% from experts. We see that there's a small width between the 25th and 75th percentile scores, meaning that they're pretty consistent. There are mild outliers, and then experts also produce results that are very poor, meaning less than 50% overlap with the truth. So that's the standard, that's the target performance, and as we can tell, experts are doing very well, but they are not perfect. So now we look at how are algorithms doing on this data set, and in particular, if algorithms do as good as experts, the problem is done. So we evaluate 11 different algorithms, and when we look at the best performing algorithm, we find that overall it doesn't do very well, but it can do quite well. So we see a low median score, but the variability is large. So it suggests that while this is perhaps not a standalone best algorithm, this algorithm can do well at times. And finally, we looked at how do untrained crowd workers do. And again, if crowd workers can match expert quality, then there's no need for an additional framework. So So we look at the results from 5 different crowd workers for each of 305 images. And what we find in orange is the results. So again, there's a higher median score than the algorithms, and there's low variability between the 25th and 75th percentile scores. But even still, with crowd workers doing better than algorithms, they're still not matching expert quality. So we now have our 3 baselines that show that we don't yet have a solution to replace experts. So now we're going to talk about how does the SAFE systems do. So for our SAFE systems, we first say how could a system do compared to standalone algorithms. So assuming a researcher wants to go with inexpensive algorithms, what we propose is that for each of the 305 images, we choose 5 of the algorithms from the 11 we explored. We let the crowd vote between those 5 algorithm options for the one that he or she thinks is the best. We collect 5 votes from 5 different workers, and then we use the majority vote per image as the resulting winning segmentation. And what we found is that when we use the simple voting step from the crowd, that we can actually find an improvement by 3 percentage points over the best of 11 different algorithms. So this inexpensive step, which can be done rapidly, so what we found is the crowd speed is actually 25 votes per minute, or with 5 votes per each segmentation, we're talking about getting through 5 segmentations per minute. We can actually get a pretty nice improvement. So next we said, well, okay, so we can do better than standalone algorithms. How about compared to human-drawn annotations? So to explore this, we start with collecting 5 annotations from 5 crowd workers. We then explore 2 different configurations with our SAFE system. So one configuration is we have the algorithm vote between the 5 crowd drawings. And the second configuration is we have the crowd vote between the 5 crowd-drawn segmentations. And then, again, we use the majority vote winner to establish the final segmentation, and we evaluate annotations. And so this shows the results. So you can see the results shown for the experts in red. You can see the results from the crowd workers in orange, from when the crowd votes on the crowd drawings in yellow, and from when the algorithm votes on the crowd drawings in green. And hopefully what you can see is that compared to standalone crowdsourcing methods, both using crowd voting and algorithm voting within our SAFE framework improves upon today's crowdsourcing. So what we find is higher median scores and fewer outliers and lower margins between the 25th and 75th percentile scores. And in addition, what we find is that when comparing the top performing SAFE system against experts, it's actually statistically similar in results. So using the SAFE system, we found that it can actually produce results comparable to segmentations produced by experts. So just to highlight visually what's going on with our SAFE systems, so here I show an example with a raw image followed by what the target is, the gold standard. And then I showed 5 drawings produced by crowd workers. I show the result from our SAFE system using algorithm voting, and then the result from our system using crowd voting. And hopefully what should become evident is that when most or all of the segmentation candidates are comparable, using the less expensive algorithm voting is a great option. However, in this next example, when we only have one, or in general, a few candidates that are good, which is typical from algorithms, then crowd voting is a great option for one to use. And finally, we highlight that for a given image, when all the input options are poor, neither algorithm voting nor crowd voting can do well. So, to summarize, we have proposed here a new segmentation framework called SAVE, which actually links crowds and algorithms together into a pipeline. And we have demonstrated that This SAVE system can produce higher quality segmentations than 11 standalone algorithms, and it can also produce expert quality segmentations. And finally, we'd like to thank NSF for funding this work. Thank you for your time.